Today, in the first part of the lecture, I will start to try to finish some exercises here on this martingale theory, and then I will turn to the course. I will come back to the Markov decision processes. Okay, so last time we were in the exercise 10, and we did the first question. I hope that it is clear because I did some mistake and then I put it afterwards this correction. So if it is not clear, I can repeat the computation. But if it is clear, I don't do it for the first question. Is okay, or do you prefer repeat again? No, it's okay. Okay, so we have seen that. Okay, yes. So we have seen that if you have this Markov chain and if you have some bounded function f, then MNF is a martingale with respect to the natural filtration of the Markov process. And in fact, you can go in the other sense. If you have the property that for any bounded function f from E to R, the process MF is a martingale, then you can conclude that X is a discrete time homogeneous Markov chain with transition matrix P. So it is just this thing that I didn't do last time, so I will do it. So I will continue this exercise. Maybe it was in the previous. Let me see, it is here. No, okay, I will repeat some new one. Okay. So, okay, so now we have that. So it is exercise 10. It is the second question. So we know that for any f, which is from E to R bounded. So now we don't assume that Xn is a Markov chain. We just know that it is a stochastic process, so a collection of random variable indexed by time. MF, okay, bounded. We know that MF is a martingale. Okay, respect to the natural filtration Fx of the process X. And so we want to show that it is that it implies that that X is a Markov chain. So the idea is very simple. In fact, for any I in E, we apply this property with the function f, which is just the indicator function of I. So it means that to X in E, we associate one if X is equal to I and a 0 otherwise. Okay, indicator function of the state I. So if you do that and you use the fact that MF is a martingale, you have that the expectation of Mn plus 1f given f and x is equal to MNF. So now if we write what is MNF, MNF by definition, it is a sum from k equal 1 to n of f of xk minus pf of xk minus 1. Okay, and so this implies in particular that, okay, I can write this, since MNF is in fact Fn measurable, I can write it like that. MNF given Fn x. So in fact, you have this equality implies that the conditional expectation of Mn plus 1 f minus MNF given Fnx is equal to 0. Okay, this is equivalent to say that the martingale is equivalent to say that you have this equality, which is here. It's exactly the same. So now, if I look at what is Mn plus 1f minus m and f. So I have the sum which goes from 1 to n plus 1 minus the sum going from 1 to n. So at the end, it remains only the last term, f xn plus 1 minus pf xn. So we have that the conditional expectation of f of xn plus 1 minus pf of xn given fnx is equal to 0, which is equivalent to the expectation of fxn plus 1 given fnx is equal to expectation of pf xn given fnx. But you see, if a random variable which is here, pf of xn, it is just a function of xn. So in fact, it is fnx measurable, so it is equal to pf of xn. And this is true, in fact, for any bounded function f. So in particular, if you apply this, so you have to remember what is this guy. If this guy is the sum over j in E of p pf xn, pxn j, fj. Now, if f is equal to indicator function of I, what you get here, you get that the probability of, because it is an indicator function, so the expectation of some indicator function is the same as the probability. So it is a probability that xn plus 1 is equal to I, given fnx is equal to, so here in this sum, since f is just the indicator function of the point I, this f of j is equal to 0, except if j is equal to I. So at the end, what remains is only p xn I. Okay, so in other words, which is equivalent to say that the probability that xn plus 1 equal to I, given, okay, I can write it like that, because it is a sigma field natural filtration of the process xn, is equal to p xn I. And so it implies that this guy is just a function of xn. So it means that this conditional probability is in fact equal to the probability of xn plus 1 equal to I given xn. Because here this conditional expectation depends only on xn, doesn't depend on the past. So it proves that xn is a Markov chain. Okay, the fact that this guy depends only on xn proves that you have this equality which is here, written here. Okay, and so this proves that it is a Markov chain, and moreover, we have that as a probability transition of this Markov chain is given by p, and so it concludes the proof. Okay. Okay, good. So now we continue to do two exercises which are important, which is this Dupes inequality here, and Dupes decomposition and Dupes optional stopping theorem. So I mentioned this Dupes optional stopping theorem. I gave some general form, but here we will prove it in some particular case, in the case where you have some bounded stopping types. So let us start with this Dupes inequality. So what we have here, we have a Zn, which is a non-negative sub-martingale with respect to some filtration Fn. So I recall you what is a sub-martingale. It means that, so in the martingale, if it was martingale, it would be that the conditional expectation of Zn plus 1 given Fn is equal to Zn. When it is a sub-martingale, it means that in average, the expectation of the process is increasing. So it means that the expectation of Zn plus 1 given Fn is bigger than Zn. And it is non-negative. So it is bigger or equal to 0. Okay, and so the Dupes inequality is something which is a bit like Markov's inequality, but you say it is something much more stronger, because here, if you look at this inequality, we say we want to show that the supremum over the sup of the zk for k less or equal to n. So it is a probability that there exists k less or equal to n, such that zk is bigger or equal to c, is less or equal to expectation of Zn divided by c. So you have to compare this inequality with the Markov inequality, which is just this one. Okay, this is the Markov inequality, but here what we ask is to prove something which is stronger, because here you see you control the trajectory during the time interval 0n, because this is the supremum of zk. You control it only by the last term, and this is due to the fact that you have a submarginal. Okay, so let us prove that. So we'll, okay, so proof is not so difficult, but see, if it is the first time that you see it, it is not so evident to find the trick. So I think it is, what is the number of the size? It is 11. Okay. So the size 11. So we add that Zn is a submarginal. So for any n, we have that the expectation of Zn plus 1 given Fn is bigger or equal to Zn. So now what we want to control, we have some C strictly positive, which is fixed, and we want to control the probability that the sup for 0 kn, k less than n of zk, is bigger than c. Okay, so now what means that the supremum, it is a supremum of a finite number of random variables, so it means that it is a probability that there exists k in 0n such that zk is bigger than c. So it is a probability of the union. And so the idea is that, okay, so it is a probability union over k equals 0 to n of zk bigger or equal to c. So of course, these events are not disjunct. So I could try to bound it by using some union bound, saying that it is less than the sum over k equals 0 to n of zk bigger than c. But then we will lose a lot, and we will do something a bit more precise. So in fact, let me call this event f and decompose the event f into some disjunct union. So the fact that saying that there exists k equals in 0n such that zk is bigger than c, it means what? It means that or z0 is bigger than c. Okay, first possibility. Second possibility, which is disjoint, is that z0 is strictly less than c, but z1 is bigger than c. Union, z0 strictly less than c, z1 strictly less than c, but z2 bigger than c. So it means that here in the first event, it is the first time that my process go up to c is 0 first time. In the second event, it is the first time that my process is going above c is at time 1. In the third event, it goes for the first time above c at time 2, and so on. And the last one is So 0C, Z1C, Zn minus 1. Small n, sorry. Cn minus 1 less than C, and Zn bigger than C. And here's the advantage is that now this F is a union of some disjoint events. Okay, I will call it this event Fk. Okay, this is F0, this is F1, and so on. And it is here the sum is going up to n minus 1. Okay, and they are disjoint. So I have that the events are disjoint, so that the probability of F is equal sum from k equals 0 to n minus 1 of the probability of Fk. And now I have to estimate the probability of Fk. Okay, so what is the probability of Fk? Probability of Fk is the probability that the 0 is less than C, Zk minus 1 less than C, and Zk bigger or equal to C. And so what we will do here is to write that, okay, on Fk, if this is, I can write it like the expectation of 1 over Fk. Okay, it is the same. And on Fk, we have that Zk over C is bigger or equal to 1 because of his equality, which is here. Yes. So it means that, in fact, I can bound this guy by the expectation of 1 Fk times Zk divided by C. Okay, it is something that we do similarly when you try to prove the Markov inequality. And now, okay, it is like that. So what I will do is that now I will condition, I can write this expectation as the expectation of the conditional expectation of 1 Fk Zk divided by C given Fk okay. But that is completely, no, it is a bit stupid, sorry. No, what you do now, yes, you make some conditional expectation, but it is, no, yes, okay. Now I will use the fact that I have some sub-martingale. So since it is a sub-martingale, I know that is Zk, because I want to control all these Fk, this probability of Fk, by something would depend only on the terminal time n. Okay, if you remember what we want to prove at the end, we want just to have the expectation of Zn. So I have to rely the Zk to the Zn. But since I have a sub-martingale, I know that this Zk is smaller or equal to the expectation of Zn given Fk divided by C, because Zk is a sub-martingale. You say the sub-martingale means that the expectation of Z, the expectation of Z k plus 1 given fk is bigger than zk. But in fact, if you think just a bit, it is implied that if L is bigger than K, by induction, you have that expectation of ZL given Fk is bigger or equal to Zk. You do it step by step, okay? So you have this property, which is here, that if you take some time L bigger than the time K, the conditional expectation of ZL given Fk is bigger than Zk, okay, which is a consequence of this one, and prove it by induction. And so it is exactly what I use here to bound this guy Zk by the expectation of Zn given Fk. Now, what I will do is that I will use the fact that Fk is Fk measurable. So it belongs to Fk. So it belongs to Fk. Because if you remember what is Fk, it depends on the random variable Z0, Z1, Z2, until Zk. So it depends only on the K first time. So it is some subset which belongs to this Fk. And since it belongs to Fk, I can use this property of the conditional expectation to put this guy inside the conditional expectation, because it is a conditional expectation with respect to Fk, and my Fk belongs to calligraphic K, calligraphic Fk, so filtration at time K. So you can write it like this is some equality here. Expectation, okay, I can put the C outside, 1 by C, conditional expectation of Zn 1 Fk given Fk. Okay, now I will use again property of the conditional expectation. I know that the conditional expectation of the conditional expectation, it is just the usual expectation. So I can write here that this is equal to 1 over C expectation of Zn indicator function of Fk. Okay, so what did we prove? We proved that the probability of the event that we are interested in, which is F, is the sum from K equals 0 to n minus 1 of the probability of Fk. And we prove that this probability of Fk is less or equal to the guy which is here. Okay, so we can bound this quantity by 1 over C, the sum over K equals 0 to n minus 1, the expectation of Zn 1 Fk. Okay, so now what I will do is that I will insert this sum inside the expectation. So I get that this is less or equal to 1 over C, expectation of Zn, sum from K equals 0 to n minus 1, indicator function of Fk. And now, since the Fk are disjoint, and the union of the Fk is equal to F, the sum of his indicator function is in fact just the indicator function of F, since F is equal to the union of the Fk, and the union of disjoint sets. So we get that this is less or equal to 1 over C expectation of Zn indicator function of F, but this guy is just in fact bounded. I can bound this indicator function, which is here. I can bound it by 1, and I get that it is less than 1 over C expectation of CF. Okay, so the probability of the set F that we are interested in is bounded by this quantity, 1 over C expectation of the F. And I recall you that this F was exactly probability that supremum 0kn of ck bigger than C is less 1 over C expectation of CF. This one, this F was exactly this set. So, okay, so the method of the proof is a bit similar to the Markov inequality, but you see there is a subtlety, which is, so there's the idea to prove this, this inequality is to think, to decompose the set that you are interested in as a union of this fk. So it is the first idea to add in order to prove the inequality. Then you have this probability, which can be written as a sum. And then the second idea, so this idea which is here, it is very similar to the idea that you have when you try to prove the Markov inequality. Then it is here that you use the sub-martingale property here to bound by like that. And then once you have this second idea to use this bound from the sub-martingale, then the rest is quite natural. You inject this fk inside the conditional expectation, and then you continue and you conclude. Some questions or some comments or some more explanation that you need? Oh, it is okay. Okay, good. Good. So we can continue with. So the next question is quite easy. In fact, is the following. So if you take a Fn martingale and you take C, which is a convex function, just that the expectation. Sorry, here it is. There is a mistake. It should be here. It should be Mn. It's a M. We'll have to correct. You assume that the expectation of absolute value of Cmn is finite. And the goal is to show that C of Mn is Fn sub-martingale. So, in fact, the argument is very simple. You just use the correct ingredient. Do you have some ideas of which kind of ingredient we can use here? So you have to remember if you want to prove that it is a sub-martingale, what you have to prove is that the condition expectation of C of Mn plus 1 given Fn is bigger than C of Mn. And what you know is that the condition expectation of Mn plus 1 given Fn is equal to Mn. It is something that I mentioned yesterday, some inequality.
I suppose Jensen inequality.
Exactly, yes, it is a conditional Jensen inequality because, okay, it is exactly this one that we have to use. Good. So you see, so question it is, so we know that Mn is a martingale, okay? Mn martingale, so it means that the expectation of Mn plus 1 given Fn is equal to Mn by definition of martingale, which implies also that for any L bigger than L, sorry, for any N, any K bigger than n, the conditional expectation of mk given fn is equal to mn. Yeah, but okay, we will not use that. But now we want to show that it is a sub-martingale. So I have to start with the expectation of C of mn plus 1 given fn. And I want to say that it is bigger than C of mn. So as you say, we can use the Jensen inequality. So if I use Jensen inequality, I will get in this direction, the inequality will go in this direction. I will say that it is, because C is convex, it is bigger than C, the conditional expectation of mn plus 1 given f. And now you say it is finished because you have this martingale property, which is here. So you have just to say that this C of mn, and so C of mn is a super-martingale. So it is a direct consequence of Jensen inequality. Which is a nice property because C can be nonlinear. For example, you can think about all the convex functions that you could imagine, and you get some sub-martingale. By applying to a martingale convex function, then it becomes a sub-martingale. Okay. That is the third question is also not so difficult. You see if you have some ideas. Now you take some Fn martingale, Mn, and you want to show something which looks like the first inequality, the first question. But now we don't assume that this martingale is positive. Okay, it can be negative, it can be positive, whatever. So we have to deduce. So it means that we have to use the previous questions to show this inequality. So do you have some ideas?
Maybe we need to show that absolute value of martingale is also martingale.
Not if you want to apply the first question, you don't need a martingale. You need just a sub-martingale. Yeah.
Okay.
So you need to show, yes, you need to show that absolute value of Mn is a sub-martingale. But isn't it something that will prove that if you start from a martingale, you get the absolute value of Mn is a sub-martingale? If you think about question 2, what are the convex functions that you know?
Well, I think that just one identity, yeah, and we take absolute value. Oh.
Absolute value, yes, but absolute value is not the identity. Yes, it is not the identity. Absolute value is absolute value. Yeah, I mean.
Yeah. Okay.
You know,
okay.
But
you're
right.
Yeah. Absolute value. Yeah. Absolute value.
Absolute value is a convex function. If I plot the graph.
Yeah. Sorry.
It
yeah.
is like that. Okay. It is not differentiable at 0. Okay. So it is. It is not 2 times differentiable, so you cannot say that the second derivative is positive everywhere because it doesn't exist everywhere, but it is convex. It is a convex function. Okay, the typical convex function which are useful are in the absolute value power p, or the exponential function is also very used full convex function. So since we have a martingale here, and we know by the question 2 that absolute value of Mn is a sub-martingale by 2, question 2, because absolute value is convex. And so if it is a sub-martingale, then you can apply the question 1, which is here, and yet you can just replace with zk, or replace it by absolute value of mk, And you see it's exactly the inequality which is written in question 3. Okay. So okay, so it is something which is very useful, that if you take martingales and you apply any convex function, like the square function, for example, then you get a submartingale. And you have this inequality, which is called Dupes inequality. In fact, the Dupes was a mathematician who developed a lot of the theory of the martingales, and there are many theorems with on martingales with the name Dupes. So this one is called the Dupes inequality. Okay, good. So okay, let us try to do.
Excuse me, what is the Dupes inequality? It's with absolute values or in
it
red?
is both.
Okay.
It is both. So we call Dupes inequality phase 1, but also called Dupes inequality phase 1. So we say that the last one is a Dupes inequality for martingales. Phase 1 is a Dupes inequality for positive submartingales.
Okay, see.
It is like the Dupes optional stopping theorem. So I gave you some form of the Dupes optional stopping theorem, but there exist different forms. So it is a generic name to denote several theorems. Okay, we will do exercise 12 if we have time. So I would like to do this exercise 13 because it is a proof of the Dupes optional stopping theorem that I presented in a general form in the course, in the first lecture. But here we will give some proof in some particular case. But the proof is interesting by itself. So, and it is based off something which is some kind of discrete stochastic integral. Okay, what is the Dupes optional stopping theorem? I recall you the Dupes optional stopping theorem say that if you start with, for example, a martingale, but it is also there is also some Dupes optional stopping theorem for submartingale and supermartingale. If you have Mn, which is a uniformly integrable, okay, maybe I can show you in the lecture. It will be simpler, just to recall you. Okay, it is here, if you remember. So in this, we add then a uniformly integrable submartingale. So in particular, a martingale is a submartingale. So martingale is a particular case. And since it is uniformly integrable, we know that it will converge as n goes to infinity to some random variable x, which is denoted by x infinity, which is in L1, which is integrable. And the convergence is P almost surely and in L1. So it is the first fact, but it is not the Dupes optional stopping theorem. It is just this one is a Dupes convergence theorem. Now, the Dupes optional stopping theorem say that if you take, so you know by the property of submartingale, you know that for any k bigger than n, the expectation of xk is bigger than the expectation of xn. You remember you have just to take this thing here. So it is the property of submartingale. So if you take the expectation on both sides and you use the fact that the expectation of the conditional expectation is expectation, you get that the expectation of xn plus 1 is bigger or equal to expectation of xn. So it means that in average, the expectation, in average, xn is increasing. And so in particular, it means that for that, if you, it is a sequence which is, sorry, I don't know what I say. It is a sequence which is increasing. So the expectation of xn is always bigger than the expectation of x0. And the Dupes optional stopping theorem tell you that you can, if tau is a stopping time with respect to this filtration, then the expectation of x tau is bigger than or equal to x0. So it means that here in this inequality, you can replace this deterministic time by the stopping time. And so just to be careful, what is x tau? X tau is defined in this way because tau is the stopping time, so it can take a priori the value plus infinity. So if it takes the value strictly less than infinity, you just replace omega by omega, you replace the time n by tau of omega. But if tau omega is equal to infinity, what you do is just that you say that xn is replaced by x infinity. Okay, so this is the Dupes optional stopping theorem, and we will prove this Dupes optional stopping theorem in the case where we assume that tau is bounded by a constant, a deterministic constant, not finite, but bounded by a constant. So it is the aim of this exercise that we now present. So let us go. So this, the proof is done in several steps. So we start with some martingale. So here I just prove the Dupes optional stopping theorem for a martingale. Okay, it is a Fn martingale, and now we consider some predictable process. So predictable process, do you remember what it means, predictable? Maybe not. It is something, it was in the first slide of the lecture. Predictable, it means that Hn is Fn minus 1 measurable. So you can deduce the value of Hn by knowing the process, if you have the information and up to the time n minus 1. So you can predict just the time after at n the value of h by knowing only by adding only the information up to time n minus 1. So it's the reason for which it is called predictable. And when Hn is Fn measurable for Hn, we say that it is adapted. Okay, it is adapted to the filtration. Like for example, any martingale or submartingale is adapted to the filtration. And okay, so we have this H, and we define the martingale transformation of H by okay, sorry, it's H here by sorry. Okay, this is off, which is too much. You define the martingale transform H. Okay, it is H circle M by the following. So it is M0 plus the sum from k equal to 1 to n of hk times the increment between the time k minus 1 time k of m. Okay, so it looks like some discrete integration. Okay, because here you can see that like some small increment, some increment of the martingale, and if you imagine that this sum is replaced by some integral, then it is like something like hk dnk. It looks like a bit like that. Okay, but it is discrete case, so this is definition. And what is the first question? Show that this is a martingale. Okay, and so the k point is that here h is a predictable process, and that m, of course, is a martingale. So we have to show that this is martingale. So we have to come back to the definition and do the usual thing. So let us do it. So what we have to do, we have to use the definition. We have to compute for any n expectation of h dot m n plus 1 given fn. And we want to show that it is equal to h dot m at time n. Okay, this of course this h dot n is iterable because it is a sum of iterable functions. So I recall you the definition, which k and k minus and k minus 1, because we assume that hk is bounded. It's bounded by a constant, so it means that this guy, of course, it is iterable because mk is iterable, it is a martingale. You multiply by a bounded function, so it is iterable. You take a sum of iterable function, it is iterable, and this one is also iterable. So it makes sense to consider this conditional expectation. It is well defined. Okay, now we go. So it is the conditional expectation of m0 plus a sum. So as you can imagine, since there is fn here, we will, and here in h dot m n plus 1, it will go until the time n plus 1. We will separate what is before n and the values, the special value for k equal n plus 1. So I write it like k equal 1 to n of hk mk minus mk minus 1 given fn. I use a linearity plus the condition expectation of h n plus 1 m n plus 1 minus mn given fn. Okay. Okay, what we can say about the first guy? If you look, the k is between 1 and n, hk is predictable, mk is a martingale. So what is the value of this conditional expectation? Do you know?
I suppose that it is expectation of m0, yeah?
Why? You mean why you say that this guy will disappear? It will be 0?
It's not true, yeah?
No, it's not true.
Okay.
But you know that the mk is fk measurable. Mk minus 1 is fk minus 1 measurable. Hk is fk minus 1 measurable. And here we are taking the conditional expectation with respect to some filtration, which is the biggest one, which is time n. So it means that this random variable, which is here, is fn measurable. Because m0 is f0 measurable, but f0 is included in fn. So m0 is fn measurable. hk is fk minus 1 measurable. It is multiplied by mk minus 1, which is fk measurable, and fk is a filtration. It is increasing. So it means that this random variable is fk measurable. And since fk, k is less than n, it is also fn measurable. And so if you remember what is the conditional expectation of z given g, if a z is a g measurable. It is one fundamental property of the conditional expectation. If z is g measurable, what is the conditional expectation of z given g?
Oh, it is just a conditional expectation of z, yeah? Or it is just expectation of z?
Z.
No, you are confused. It is z in this case. Okay, what you say, it is when z is independent of g, then it is the expectation of z. Okay, because think a bit about what is the meaning of conditional expectation. G is information, and we say what is the best this conditional expectation, which is here, represents the best approximation of the random variable Z by knowing G. But if the Z is G measurable, it means that you have all the information to know Z. So given G, given the information in this sigma field, Z is the best approximation. Cannot approximate by something better than itself.
Okay.
So
in the brackets, we will have MK, yeah?
Do you mean MK?
MN, yeah?
Where here?
At the bottom left. Yeah, so everything will cancel, yeah?
No, not will cancel. Here it doesn't cancel. It is just what is inside is just here. You see,
okay.
It means that taking the conditional expectation doesn't modify nothing about the random variable.
Okay.
This it is a sum, so it is Fn measurable. So like if this is a role played by Z. Z is a G measurable, you have this inequality. Here, the G is Fn, and the Z is this total random variable. And the thing that you have to realize is that this random variable is Fn measurable. It is Fn measurable because it is a sum of random variables which are Fn measurable. M0 is F0 measurable. And F0, you have some filtration. F0 is included in Fn. So it is also Fn measurable. Hk is Fk minus 1 measurable, but k minus 1 is less than n. So it is also Fn measurable. Mk is Fk measurable, but k is less than n, so it is Fn measurable. Okay, so it's the reason for which it is Fn measurable. So the conditional expectation will not change. It would be okay, good. It would be the same. Mk minus Mk minus 1. Okay. Now, here again, we have to use some property of the conditional expectation. You have to remember that Hn is predictable. So it means that this Hn plus 1 is Fn measurable. So if it is Fn measurable, what can you do? You know, it is in the list of the property of the conditional expectations that you have to know. You don't remember? Since this guy is Fn measurable, so it is Fn measurable with respect to this one, which is not the case of his Mn plus 1. No, Mn plus 1 is time n plus 1. So it is Fn plus 1 measurable, but it is not Fn measurable. But this guy here, since H is predictable, it is Fn measurable. So it means that you can put it outside of the conditional expectation like that. Okay, so in fact, you can write it Hn plus 1 expectation of Mn plus 1 minus Mn given Fn. Because it is Fn measurable. And now, by the martingale property, can you tell me how much is it? This conditional expectation.
Maybe.
Well, it should be 0, yeah?
Yes, exactly. Yeah, it is 0 because it is marked. So it means that the last term at the end, it disappears. And if you look at this guy, the first guy, which is here, is exactly h dot m at time n by definition. So we prove that it is a martingale. Okay, so usually to prove that something is a martingale, we have to use all these properties of the conditional expectations that I mentioned, which are, I gave you some precise page where you have the list of all the properties of the conditional expectation. It is something which is fundamental in when you work with some conditional expectation. Okay, so we prove that it is a martingale. So here H has to be predictable and bounded, and M has to be a martingale in order that it is true. So we'll go to the second question. Okay, by using the previous question, show that for every stopping time tau, the stopped process, okay, if is n wedge tau means is something which is very used in probability. It is the infimum between n and tau. So it is, we asked to show that it is martingale by using the previous question. So it means that we have to write this m tau, this process, this new process, as a martingale transform of the martingale. And then we will conclude by the one that it is a martingale. So, but let me comment a bit about this stopped process, why it is called the stopped process. Maybe just a picture. So m tau is a new process, stochastic process, which is equal to mn tau. How it is defined? Mn tau, it is m infimum between n and tau. So it means that it is mn if n is less or equal to tau, and it is m tau if n is bigger or equal to tau. So tau is a stopping time, and we assume, if you remember, here we assume that we assume nothing. Okay, we assume nothing for the moment. So you see, if tau, this process is well defined, because if tau is infinite, it can be infinite, then you are in this situation here. So you define it by mn. If tau is finite, so there is no problem to define this m tau. You define it like when you fix the omega, small omega, you say that it's m of omega index tau of omega. And if you make a graph, okay, let me make a graph of summarization of my stochastic process. So here I have n, I have time 1, time 2, and so on, 3. So my process is like that. So you go there, go there, go there, go there, so on. And tau is a random time. It is a stopping time. So it is a random time. So imagine that in this realization, tau is here. Oops. Tau is here. So what is so this is a process mn. Okay, at each time, it is a realization of the process because this is a stochastic process, so it is random variables. But now, what I will do is that I will plot what is this process mn tau. So you see, if n is less or equal to tau, then it is just the initial process. So it is this process. But then, if you are now in the situation where n is bigger than tau, then what you do is that you just stay constant equal to the value that you reached at time tau, m tau. So it will be, afterwards, it will be like that. Forever. Okay, so it's the reason for which this is m tau n. The reason for which it is called a stopped process. So it means that at time tau, you stop the process and you stay constant to the value that you reached at time tau, at this random time tau. Okay, it is clear then why it is called stopped process. It's just for that. So now we want to show that it is this guy is a martingale. Okay, so and the idea is to use question 1. So we have to show that this m tau can be expressed as a martingale transform. So we'll try to write it like martingale transform. So let us look at what is m tau. So it is what I wrote here, and I wrote the definition is here. But now what I will do is that it can be quite natural is to decompose according to the value taken by tau, because I need to create some sum if you want to see it as a martingale transform. So I will say that it is the sum from k equal 0 to n, so 1 tau equal to k. So if is or maybe n minus 1. Yes. So if tau is equal to k, so it means that we are in this situation. Okay, here write strictly. Okay, so tau is strictly less than n, so it is just m tau. So since tau is equal to k, it is mk. And there is a second possibility that tau now is bigger or equal to n, and so in this case, it is just mn. Okay, so now, okay, what I have here, it is it looks a bit like some martingale transform, but in the martingale transform, it will be better to have here some increments of mk. So the idea will be to perform some discrete integration by part by writing this guy as some increment and then performing some change of variable to make some discrete integration by part. So what we do with that, we can say that is this guy 1 2 equal to k. You can say that it is the same. I think that tau is bigger or equal to k, but is not bigger or equal to k plus 1. So do you agree with that? I just write that tau bigger equal to k means tau bigger or equal to k, but not tau bigger or equal to k plus 1. Okay. You agree, or is it yes? I assume yes. So now what I say is that I can rewrite, I decompose in 2, and I will perform some integration by parts. So I say that it is a sum from k equal 0 to n minus 1, indicator 2 bigger or equal to k and k, minus the sum from k equal k, now it is 0 to n minus 1, 1, 2 bigger or equal to k plus 1, and k, plus 1, 2 bigger or equal to n, and n. Okay, now in this second sum here, what I do is that I will perform some change of variable, changing k into k plus 1. So it means that the sum will start from 1 and will go until n. And then here it would be k, and here it would be k minus 1. Here I perform just a change of variables. So now the idea is to regroup term together. We can not do it exactly because you see the sum is here n, and here it is 0, but we can isolate these two terms and group together the other ones. So it is a sum from k equal 1 to, say, n minus 1, 1 over 2 bigger or equal to k mk minus mk minus 1, but it remains the term 0 plus 1, 2 bigger than 0 and 0. I have to subtract the term that I forgot here, n, which is indicator of 2 bigger than n minus 1, and it remains the last term plus 1, 2 bigger or equal to n of mn. Of course, this indicator function is equal to 1 because saying that tau is positive, since tau is a stopping time, it is with values in n, union infinity, so it is always positive. So this indicator function is in fact just a function 1. Moreover, you can see that you can regroup this guy together, and you get exactly this guy, but evaluated for, sorry. I don't know what happened. Okay, they can group. I can take this guy with n, and it is exactly the same guy that is the guy with k equal to n. So I can write it like the sum from k equal 1 to n, 1 tau bigger or equal to k, mk minus mk minus 1 plus m0. And if you look at this form now, I rewrite this stopped martingale as a martingale transform. So it is exactly 1 tau bigger or equal to k dot m time n. So it means that it is, I can write it in a different way. It is h dot m at time n with hk, which is equal to 1 tau bigger or equal to k. And if I want to apply the previous the question, the first question, I have to be sure that this hk is bounded and is predictable. So the fact that it is bounded is trivial because it is with values in 0, 1, this indicator function. So it is trivially bounded by 1. Now, why is it predictable? Predictable means that hk is fk minus 1 measure. So I have to be sure that this guy is fk minus 1 measure. So I have to show it tau bigger or equal to k. I have to show that it is fk minus 1 measurable. So what I know, since it is a stopping time, I know that when tau is less or equal to k, it is fk. It is in fk, this event. So, but here it is tau bigger or equal to k, but I can write it like the complement of tau less or equal to k minus 1. Okay, since tau is with values in the integers, then tau bigger or equal to k is exactly the same as saying that tau is less or equal to k minus 1. but to say that it is the opposite of tau less or equal to k minus 1. And this event is in fk minus 1 because tau is a stopping time. And so since fk minus 1 is a sigma field, you know that the complementary of any event is in the sigma field. So at the end, this is also in fk minus 1 because fk minus 1 is a sigma field. So we proved that this hk is predictable. Hk is bounded and predictable. And it is implied by the question 1 that h dot m, which is in fact equal to m tau, is a martingale. Is it okay or there are some questions? So I know that I think I will finish because the last question is not so long, and then we'll make the break. But is the arguments are clear here, or there is something which is not completely clear for you? Yes or no? It is clear. Okay, good. So, okay, m tau now is a martingale for any stopping time. So let us see what is the last question. Prove the Dupes optional stopping theorem for discrete time martingales for bounded stopping time. Okay, so we need to show, what we have to show is that the expectation of m tau is bigger than the expectation of m0. But we assume here that tau is less or equal to k, where k is a constant, or real constant, positive constant, which is fixed, okay, which is not random. And okay, we will see that it is very easy because, in fact, sorry, with this for martingales, we have to show the equality tree. Yeah, here we assume that it is martingale, so sorry, we have to show equality. Because we assume initially that M is martingale, so the Dupes optional stopping theorem for martingale is equality, not inequalities. Okay, let us show it. You will see that it is quite direct application of the previous question, because what we prove is that m tau is a martingale. So if it is a martingale, the main property of a martingale is that this expectation is constant in time. So expectation of m tau n is equal to the expectation of m0 tau for any n. Okay, it is the main property of martingale. It is conditional expectation of mn plus 1 given fn is equal to mn. But if you take the expectation on both sides, you get the expectation of mn plus 1 is equal to the expectation of mn. And so it is constant for any n. Now we know that tau is less or equal to k, where k is fixed. So this one is expectation of m infimum between 0 and tau. So of course, the infimum between 0 and tau is 0, so it is expectation of m0. So this is for the right-hand side. And now it is phase 1. So phase 1 is equal to expectation of m inf between n and tau. But here, I would like not to have this infimum, I would like to have tau. So do you see which n I could, this is true for any n, okay? Which n I could take in order that I get exactly n tau? this equality is true for any n. Okay, but now I can choose n. Okay, if I think n is equal to 0, I get expectation of m0 is equal to expectation of 0. But now I can take n as I wish. And tau is less or equal to k. No ideas?
You can take k.
Yes, exactly. Right? You take n equal to k because it is true for. And then if n equal to k, the infimum between n and tau is just tau. And so you get that this guy is equal to expectation of m tau. Equal to expectation of m0, and so the thing is proved. So you see it is true for tau if tau is a bounded stopping time. You can also, from that, you can also show it if M is a bounded martingale, because if it's bounded martingale, what you can do is to send N to infinity and use the dominated convergence theorem. If N was to infinity here, in this expression, M infimum between N and tau converges to M tau. And since the martingale is assumed to be bounded, then you have the convergence and you get exactly the same conclusion. So it is two cases which are not too difficult to prove. The case where you have only the uniform interoperability, it is a bit more difficult, but the ideas of the proof are here in this simple case. Okay, so perfect. So okay, I will stop here now. We will make a break of 10 minutes and I will come back to this Markov decision processes, and then I have finished with this first chapter of exercises. Okay, I will not finish all the exercises, but if you have some question about the exercises, which is in chapter 1, you can ask me. But try to you can try to do it to train yourself. Okay, so we make the break now, and in 10 minutes we come back, if you agree.
Okay.